All right, so in this video, we're going to do an introduction on precision landing, what it is from a high level perspective, what it allows us to do, why it's important, so a bunch of fun stuff. So what is precision landing? Like how are we defining that phrase? Well, in order to understand how we're defining the precision landing phrase, we should look at it from a relative perspective. So, most conventional drones have a GPS attached to them. And those GPSs allow the drone to land, around plus or minus 10 feet on a landing target on the ground. For many applications, that might be good enough. That might be precise enough. If you're a drone surveyor and you just want to scan the field, take a bunch of images, and land the drone in a general area, that's probably good for you, plus or minus 10 feet. But there are other applications that require a much, much more precise error rate than plus or minus 10 feet. So we're going to define precision landing here as any landing methodology which is accurate to around plus or minus 10 inches or better. So why is precision landing important? What might be some of those drone applications that require that precision landing? Well, there's a lot of things like maybe package delivery, maybe a Amazon consumer of the future has a little target in their backyard that the drone that's delivering a package must identify and land on. Maybe precision agriculture, maybe there's a crop spraying drone that needs to land in a very precise location so that it can autonomously refuel or refill its pesticide containers. Maybe, drone in a box applications where the drone leaves its charging station in a little box, does its mission, and it must return into the box. And, in order to do that, it needs to be able to have a very precise landing methodology. And indoor flight, we mentioned that GPS has plus or minus 10 feet accuracy for landing, but indoors, you don't even have GPS. So you would 100% need some form of precision landing to be able to actually even land the drone indoors. So let's cover a couple of the main precision landing methods that are currently being done. There are two main methods, and there are pros and cons to each. We'll go over both of those. The first method in purple, that is any camera empowered with OpenCV for tracking an image on the ground. It's a very simple method. It can be very cheap, as we'll see, but there are some drawbacks to it. We'll cover those. Then the second one is IR lock for tracking an IR emitting beacon on the ground. This is more of a plug and play application, but regardless of which method you pick, either one with a well-tuned drone should be able to have a sub 10-inch consistency for landing within a desired target. And also both of these methods consist of there being a camera on the drone side that is tracking some object on the ground where you want to do your precision landing. So with the first method, we have a simple camera here, and it's tracking some image on the ground. This is an Aruco marker. That's some foreshadowing for what we'll be doing later on in the course. And then that second method, there is a Pixie Cam fixed to the drone, and that is tracking an IR beacon on the ground that is powered by maybe a LiPo battery or something, but it emits infrared light that the Pixie Cam is tracking and is specially fitted with an infrared lens to be able to find those rays. Now we can start to see one of the biggest differences between these two methods. The first method is extremely cheap. All you need is some camera that's around $20 if you're using a PiCam. And then the target on the ground, well, that just costs as much as your paper costs, because you can just print that target onto a piece of paper and you're good to go. You don't need to power that target with a battery or anything. You don't need to purchase it from a company. You can just print it off. In the second method, the camera is a little bit more expensive. It's $120. It's specially fit with that IR lens, so that's a little expensive. And then the beacon, that's not a piece of paper anymore. That's a very complex beacon that emits IR light, and it needs to be powered by a LiPo battery. So the price points of both of these methods are very different. So let's see what that means in terms of performance of these two methods. Well, the altitude range on the first method, being the camera powered with OpenCV, the range, it sort of depends on how you build it. So the altitude range is actually a function of the ground target image size. So that Aruco marker we had in the last slide, is it a huge marker? Is it a small marker, a couple inches? That's a factor for the altitude range. And then another one is the image resolution that you are running your OpenCV scripts with. The higher the resolution, the higher the altitude you will be able to perform that precision landing from. But basically, like I already said, any altitude should work given a high enough resolution and the right size marker is used. But this does require manual setup and engineering. So it doesn't work just out of the box. Well, the altitude range of the IR lock is a little bit more straightforward. The range is anywhere from 0 to 60 feet. So around 20 meters. And this range, it works out of the box. It's not like the OpenCV camera method where you have to configure everything. Basically, it's a plug and play solution. One thing to keep in mind though, while we're discussing altitude ranges, which is the range of your precision landing, which means the maximum altitude from which you can start a precision land. That depends on the range of your rangefinder. So if you were using, like I have pictured here, a T8 Mini rangefinder that has a maximum range of 6 meters or around 20 feet, if you paired that with the IR lock solution, that would now be your maximum altitude from which you could perform that precision landing. Even though the IR lock solution is capable of working from much higher altitudes, the bottleneck of the precision landing is the range of your rangefinder. So let's sort of summarize the pros and cons for these two methods. With the first one, the big pro is that it's super cheap, right? $20 or whatever your camera cost that you want to use. And another pro I should probably have mentioned here, the altitude is basically boundless because you can always increase the size of your marker on the ground. Cons though, and this might be the other side of that hidden pro that I just mentioned, this method does require engineering it, and it doesn't really just work right out of the box. You need to know OpenCV, you need to know, how to track that marker and feed in the error coordinates to the drone's ArduPilot firmware and all that stuff. So you need to put your engineering hat on if you want to do method one. And the other con for this method is it doesn't work in the fog or in the dark. The camera must see that target. Now for IR lock, the pros, you can just plug and play. You just plug it in, everything should work. Might be a few parameters or settings to set up on the Mark I beacon, but essentially you don't really need to put your engineering hat on with this method. You just put it on and it should work. And this method actually can see through fog, so it's much more resistant to weather conditions, and it works in the dark as well. The con here is that it's $300 after you account for the $120 camera, the $160 Mark I beacon that I have pictured here, and the $20 LiPo battery that you need to power your Mark I beacon. So it's around $300. And the other con is that the range of precision landing is limited. It's bounded at 0 to 60 feet. All right, so in this video, we're going to get into a little bit of simulation and gazebo. So what is gazebo? Well, here's another by the book definition. Gazebo is a 3D dynamic simulator with the ability to accurately and efficiently simulate populations of robots in complex indoor and outdoor environments. But wait, there's more. Gazebo offers physics simulation, a suite of sensors, put that one in italics, that's an important one, and interfaces for both users and programs. So basically, Gazebo is a simulated world that obeys the laws of physics, and this is where we can test robots or drones. So what can we do with Gazebo? Um, well, it's pretty cool. We can actually fly the Ardupilot firmware, the real code, on a simulated drone in the Gazebo world. Now, if you took the drone programming primer class, you know that the simulated drone is called CIDL. So we're basically connecting CIDL with Gazebo, and we can test that simulated drone in the 3D world. And if you look on the right with that picture, that is actually a picture of the 3DR Iris, and that is sort of the standard drone model that is used for Gazebo to test Ardupilot firmware. So what else can we do with Gazebo? Well, we can, just like we could in the drone programming primer, we can use and test Python DroneKit scripts on our computer to actually control the simulated drone. Now you might be saying, cool, this was already a thing we could do with CIDL. Why do we need to, visualize it? Well, for one, the Gazebo physics engine is very, very impressive and is maybe a little bit more realistic. But the other very important thing about Gazebo is that you can simulate various sensors and experiment using them to control or influence flight. Okay, so why do we need Gazebo in this course? Well, we know that for our capstone project, our Tacocopter, precision landing is going to be a very important element of that mission. So Gazebo is going to help us test our precision landing scripts. We can actually access that simulated camera feed right in a DroneKit script where we can do some OpenCV computer vision based control on the drone. So basically Gazebo is paramount for testing our OpenCV precision landing scripts and before even using it on a real drone. So what are the benefits? Well, this is kind of just recapping, but it saves time. Like, it really saves time. Just imagine that you have this new OpenCV script that you want to use with DroneKit to control the drone, and you didn't have a way to test it, so you just had to go out to the field and test it on a real drone. Well, you go out to the field, it takes 10 minutes, 15. It takes another 5 to make sure all the sensors are working correctly, and then another 5 whenever you try and run your Python script and you have a syntax error. So, it just really allows you to rapidly prototype right from your computer, so you don't have to make or find all those mistakes out in the field. It definitely saves money. Whenever you're experimenting with new DroneKit Python scripts that'll actually control the drone, those situations have a much higher likelihood of you crashing the drone for the drone doing some crazy behavior that you didn't expect. Well, we want to find those crazy scripts in the simulated world before we go out to the real world. And it's the last one, save a limb, kind of tongue-in-cheek, but if the drone did go crazy out in the field while you're testing a new script, well, you have, as many in the Ardupilot community would say, you have a Psycho Wasp drone that's just out of control, and it can be very dangerous. So again, you want to be able to isolate those crazy flights in the simulated world. Okay, so Gazebo does require a decent amount of computer hardware. Let's go over what that is. So with memory, or the RAM, I would recommend 4 gigabytes. That's kind of the sweet spot. You could obviously go more, but at 4 gigabytes of RAM, you're getting a lot of the good behavior out of Gazebo. I've tested it with 2 gigabytes of RAM, and it works. It's kind of pushing it a little bit, but it's still maybe getting 70% of the performance. At 1 gigabyte, I mean, it still runs, but it is with pretty bad performance. And what do I mean by bad performance? Well, the rate at which the simulated world is playing is maybe at 20% of a real-time speed. So it looks like everything's moving in slow motion, which is fine if you have the patience for it, but I personally don't. Processors. Again, 4 cores is probably recommended. I have also tested with 2 cores, And it seems to work pretty good still with 2 cores. You know, it's not the perfect performance, but it's still doing a good job. With 1 core, it also runs, but again, with bad performance. So if you have the recommended computer hardware available to you, definitely use that. If you don't, you might have to experiment around a little bit. Now, the required operating system is actually Linux. So if you have a Windows or Mac PC, you are going to need to set up a virtual machine. The suggested distribution is Ubuntu 18.04. It will work on other distros, but that is what we will be using in this course. All right, so how should you go about approaching this gazebo section? Well, you know, you're likely one of these 2 people. You're either a Drone Programming Primer graduate, shorthand DPP, or you are new to the dojo, or you haven't taken that course. Well, if you are a Drone Programming Primer graduate, then good news. You should already have an Ubuntu virtual machine and VirtualBox already configured. You have knowledge of DroneKit scripts, and you have dependencies like DroneKit, MavProxy, ArduPilot, and other things already installed on that image. So this course picks up from the end of the Drone Programming Primer. So if you've already taken that course, you can simply use that virtual machine from the Drone Programming Primer to follow along in this course. If you have not taken the Drone Programming Primer, well, you're going to need to set up a Linux virtual machine. So I am actually providing access to 2 already configured virtual machine images. And with those, you're going to be able to just download those from my Google Drive and then import them into VirtualBox. So the first image is going to be the virtual machine that is from the end of the Drone Programming Primer. So you've already downloaded everything like MavProxy, PyMavLink, DroneKit, and ArduPilot. So those dependencies are already resolved, and the DroneKit scripts are already written. So that is the first image. And the second image is the virtual machine solution key for this course. So every script we're going to write in this course has already been written and tested, so you know it works. And all of the dependencies we're downloading in this course have already been installed and resolved on this virtual machine image. So here's what I recommend you do in this section. You should download both images from my Google Drive, and you should then create virtual machines for both of those in VirtualBox. Then you're going to use that first image, the one that is the end of the Drone Programming Primer, to write along with the scripts in this course. So you're going to write the scripts, and you're also going to have to install all of the new dependencies in this course, things like Gazebo and ROS. Then you can use that second virtual machine image, the solution key, for investigating any of your mistakes. Maybe you were trying to code along with the video, but you did something wrong. Well, you can check out that same file you were trying to write in that second image, the solution key. Or maybe you're having a difficult time resolving a dependency. You can also check out how those dependencies are situated in that second virtual machine image. So in the next video, I'm going to walk you through how you can actually import one of those images into VirtualBox. It's going to be a .ova file, and it's pretty cool. You don't have to download, a fresh install of Ubuntu or anything like that. You simply just import that OVA file, and voila, you have a new virtual machine on your computer. Okay, so in this video, we are going to download VirtualBox. What is VirtualBox? Well, that will allow us to run a virtual machine on whatever operating system you're using. So head on over to virtualbox.org/wiki/downloads. And then here, based on what operating system you have, click on that. So I'm on a Windows machine, so I'm going to click this, Windows Hosts. And it's going to start downloading the installation file. And then once that's downloading, go ahead and click on that, and that'll start up the installation wizard. So we'll click Next, Next, and let's see here. Let's have all of these check marked. And then we'll read this warning. It's just telling us that our network connections will temporarily be disconnected, so we'll hit Yes here. And then we'll click Install. So that'll take a little bit of time to download, and then you'll click Finish at the end. And once that's finished, you should be able to go in your search bar and type VirtualBox. And there it is. If you right click it, you can pin it to the taskbar so that it's always available here. That is if you're on a Windows machine. VirtualBox should work the same if you're on a Macintosh or Linux computer as well. So in the next video, we're going to set up a virtual machine that we're going to use in this section to perform our gazebo simulations. Alright, so in this video, we are going to set up our virtual machine that we'll be using to perform our gazebo simulations for our drone. In the lecture notes for this video, you will see links for a Google Drive to 2 files. Both of those files are pre-configured .ova files that you can simply import into VirtualBox. And when you import them, you have a virtual machine ready to go. The second Google Drive link I have listed, that is going to be the solution key environment. So every script that we're going to write in this course is already pre-written and is located in that virtual machine image. And every single dependency that you will need to run the code is also already pre-installed. That first Google Drive link is actually the end point of the drone programming primer. Feel free to download both of those images and import both into VirtualBox so that you can use that solution key if you get stuck in the virtual machine that you're using to write all the scripts. So once you've downloaded those OVA images, how would you import them into VirtualBox? Well, you would click File and then Import Appliance. Okay, and then here you would supply the path to that OVA image that you just downloaded. Yours will likely be under Downloads. And these are pretty massive files, right? They're anywhere from 4 to 10 gigs. So we're going to click on the OVA image that we want to import, and then we'll hit Open. Then hit Next. Now let's name this. You can name it whatever you want. I'm just going to call it Taco Copter. And here, the CPUs, this you will have to change. This will be dependent on your particular computer. So what I recommend doing is supplying anywhere from 25 to 50% of the CPUs that are available on your computer for your virtual machine. So if you have 8 CPUs on your computer, maybe give anywhere from 2 to 4 CPUs for your virtual machine. And use that same rule for the RAM. So if you have like 16 gigs of RAM on your computer, then maybe give anywhere from 4 to 8 gigs of RAM for your virtual machine. And then we'll keep these things all checked. And let's also hit reinitialize the MAC address of all network cards. And then we will hit import, and this will start creating that virtual machine that we will store in VirtualBox. And that'll take a little bit of time to import, so just wait for that to finish. All right, then once that's finished importing, you have your new virtual machine here. Again, I suggest importing both of those images, one for the solution key and one for the environment you're actually going to write the scripts in. But then we would just double click on that virtual machine to boot it up. And here we go, we're loading our virtual machine. And here we go, here's our login screen. Our username and password are both Drone Dojo. And here we are, here's our environment. Alright, so in this video we are going to go ahead and install all of the dependencies that are required to run the scripts in this gazebo section of the course. Now first thing we're going to do is install OpenCV, and we'll paste in this command here on a terminal. We are in our virtual machine right now, and I will grant access to this installation list of commands that we have to run. So let's hit enter here, and that'll take a little bit more time for you. So the next thing we're going to install is Gazebo 9. We are using, let's see, just to show you guys, we are using Ubuntu 18.04, so we should be using Gazebo 9. So let's paste in this command here. Go ahead and type ES. And this one will take a little bit more time to download. All right, now once that is finished, you should be able to type gazebo and then hit enter. And then we'll see this world here. It's a blank world. We'll go over what all of this stuff is in a later video, but this should be pulling up now. We're going to go ahead and close that. And there is a common error that appears to be happening with Gazebo 9 on Ubuntu 18.04 right now. So let's type sudo vi and then dot ignition fuel config YAML. Okay, and we're going to go down to URL, and we're going to replace API with fuel, and then over here replace fuel with robotics, and then save that. And that error and rest request will go away the next time we launch Gazebo. Okay, now let's install this step number 3 to our virtual machine. Let's actually go into course root, and then let's type git clone, or let's actually just paste that. And what ArduPilot Gazebo is, so we pulled up Gazebo, right, in that after we finished this long install, and we had that gray empty world. Well, what we're downloading now is actually going to populate Gazebo with a world that contains a drone that can run the ArduPilot firmware. So we have finished downloading that. Now let's go into ArduPilot Gazebo, and let's type make dir build. Then let's go into build, and then type cmake ... and looks like you might have to install it. So let's type sudo apt install cmake. Hit yes. Okay, then once we have cmake installed, we'll type cmake ... from the build directory we just created. Now we'll type make -j4. Okay, now the last step of this third installation is going to be sudo make install. All right, now we are good with that. Now let's go ahead and set up some environmental variables in the .bashrc file. So let's go there now. Gotta have something there, right? Okay, so now let's scroll to the bottom of the file, and then let's type export gazebo resource path equals, and then we'll fill that in a sec, and then gazebo model path equals. Okay, so this is what we just downloaded, ArduPilot Gazebo, and this is actually going to be one of the key paths that we will need to have in Gazebo resource path environmental variable. It'll tell Gazebo about the media folder and the worlds folder that we need for Gazebo to operate correctly. So we'll copy in this path of ArduPilot Gazebo, and we can put it in quotes. It doesn't really have to be. And then let's also do that same path, but now end it with worlds. Okay. And then let's do one more path, and that is actually going to be the USR share gazebo-9. Okay. So let's use this path as the last path in this environmental variable. There we go. Now for Gazebo model path, let's paste in that path and then do /models. Okay. And then let's also add the user share gazebo-9 models path under the gazebo model path environmental variable. And again, this is just letting Gazebo know where it needs to search on our file system to find the relevant model files and the relevant resources. And let's do one more thing. Let's say source, and then usr share gazebo-9, and then setup.sh. And this will set some additional environmental variables, but we need to edit this file real quick because it's going to do some things we don't want it to do. Okay, so let's save that. And now let's type sudo vi, and then let's go to that file. Okay, you see here it's setting the Gazebo resource path and it's setting the Gazebo model path. Well, we're already doing that every time we open a terminal. So we don't want this file to do that for us. So we're going to delete the Gazebo resource path and the Gazebo model path lines. And then let's save that. Okay, so now we have our environmental variables set up for Gazebo. Now let's install ROS. Now the installation steps for ROS can look a little difficult. I have grabbed the instructions for installing ROS from their Wikipedia here. All right, so let's run this first command here. And this will add a new source list so that we can download packages from it. And now let's run this command, which will give us a key so that we can access that new package source. Now let's actually run sudo apt update on our terminal. So we'll type sudo apt update, and this might take a little bit of time. All right, now after that is done, let's install ROS Melodic. Now it's important that you install ROS Melodic with Gazebo 9, so that's what we're doing here. So we'll type that command, and then this might take a little bit of time as well. All right, now that install for ROS actually takes quite a bit of time, but after that is done, let's go ahead and go back into the bashrc file. We have another thing to configure. So let's scroll to the bottom, and we're going to source another setup file. This one will be for ROS. So we're going to say source opt ROS melodic, and then setup.bash, and then hit save. And then we'll close that, close this terminal, and then open a new one. So that will initialize those changes that we just did to the bashrc file. And now let's install some supplementary packages for ROS. And then let's install Python ROSDep. And let's run ROSDep init. And now finally, ROSDep update. All right, so now we have installed ROS and we have installed Gazebo. Those are two separate entities, but used together they can be pretty powerful. So we're going to install something called Gazebo ROS with this command here. And this is actually, might be getting ahead of myself, but this combination is what will allow us to access the Gazebo camera. We have to use ROS to access the Gazebo camera. Okay, so in this video we should have Gazebo already installed. So here we're going to explore the Gazebo environment a little bit. So let's pull up a terminal and let's type GAZ and then hit tab. Just make sure that auto completes, and that means you have it installed. So what has it launched? Well, here is the Gazebo user interface, and the world it's displaying right now you can see here, but you know, it's this empty, cold, gray world, right? And we came here to simulate drones. We need an Ardupilot quadcopter. So it would be great if we had some sort of file, some sort of world file that we could load up with Gazebo that would contain within it objects like a drone that we wanted to simulate. Well, lucky for us, we do have something that we could load up with Gazebo just like that, and that is called a world file. So by the book definition, the world file contains a description of the world to be simulated by Gazebo. It describes the layout of robots, sensors, light sources, user components, and so on. Okay, so we know that we can get rid of this cold, empty, gray world. Okay, but where are these world files? What a great question. Well, in the installation video, we downloaded a ArduPilot Gazebo repo. So let's go to course root and ArduPilot Gazebo, and let's go into the worlds directory. And here we are. Let's go ahead and list that. So here is a list of .world files that define a world that we want to simulate in Gazebo. So that's great. Now you might be asking, how will Gazebo know about the location of these world files? Well, also in the previous video, we defined a very important environmental variable, and that was the Gazebo resource path. Okay, let's hit enter here. And here you can see that one of the paths we have listed points at this worlds directory we were just in. So that means that we can call Gazebo and reference one of these files in this worlds directory without having to be in this worlds directory. Okay, so let's just, to drive the point home, let's just go completely out of that directory. And now let's launch Gazebo, and let's launch it with the Iris Arducopter Runway World. So let's type Iris Arducopter Runway .world. All right, let's do that. And now it should be loading up. Let's see, drum roll please. A non-gray empty world, and we can actually see our drone here. So that is sweet. Okay, so now we're good to go. This is all of this stuff, everything we're looking at was defined in that world file that we just launched. The layout, the picture of the runway, the drone model, everything was predefined in that file. So now if we want to call this environment, we just call it with that world file. So let's look around the user interface a little bit. There are two main important little data trackers here at the bottom. Let's look at frames per second. Now this might vary according to the hardware resources you have dedicated to the machine running Gazebo. But if it's kind of low, like even 3 or 4 frames per second, you might want to go ahead and make sure shadows are turned off. So in Gazebo, shadows are actually being simulated. We can actually turn that off. And how do we do that? We go to Scene and then Shadows. So right now they are enabled. So if we uncheck that and then go away, you'll notice the frames per second jump immediately. So for our purposes with what we're doing with our drone simulations, we don't have to worry about shadows. So let's make sure shadows is turned off so that we get better performance. The other thing you should look at is the real-time factor. And this is the fraction of speed at which this world is being played back to us in real time. So if this is at 1, then the world is progressing at normal speed. If it's at 0.42, that means the world is kind of slowed down a little bit. And this might also be limited according to the computer resources you dedicate for Gazebo. But what you'll notice is, and I'm getting a little bit ahead of myself here, so don't worry about this part, but if we actually launch our CITL vehicle by launching CITL from ArduPilot, the real-time factor jumps up appreciably. It jumps up quite a bit. So let's just go ahead and do that real quick to show you that the real-time factor, you'll get a pretty big boost out of it once you launch your Cittal vehicle. All right, so now Cittal is booting up, and you'll notice the real-time factor started to spike up pretty high. It went from around 0.4 to now 0.8 and still climbing. By the end of the launch, it should be pretty close to 1. So if you're at 0.4 and you haven't launched, or if you're at a low real-time factor and you haven't launched your Cittal vehicle yet, don't worry about that. Now, if you had a limited amount of computer resources available to dedicate to this machine, and you have a low real-time factor, I mean, the simulation will still work. It'll just be played back in a very slow speed. So it doesn't mean that you can't run the simulations. It just means I guess you'll need a little bit more patience. Okay, so now let's cover how to move around this world with the mouse. Okay, so if you click with the left clicker of the mouse, you can drag across the view, and it's with the current zoom factor and the rotation. If you hold the right key down of the mouse, the right clicker, and you go up, it'll zoom in, and then if you go the other way while holding the right clicker, it'll zoom out. All right. And then the last thing is the scroll wheel. If you hold the scroll wheel and then you rotate, you can actually change the rotation of the view in Gazebo. All right, so I would spend just a little bit of time getting familiar with that. It's you definitely want to be able to move around the environment and watch your drone fly. And the last thing we're going to cover in this video is models. So here, if we go to Insert, we can see a bunch of models that we can insert into this world. And we have things like an ambulance if we wanted, and you just click on that and drag it in here. Oh, let's bring in a beer. You know, put a beer for that passenger driver. Cafe table. So there's a bunch of different models that you can insert into the world that you are currently simulating. Well, how? Oh, look at here. We also have an iris with ArduPilot. So here we go. Now we have 2 little drones. So all of the objects that will be in the simulated world, these are going to be models. And you might be asking, how did Gazebo know to look for models in this location and this location? Well, in addition to the Gazebo resource path environmental variable, we also set up something called the Gazebo model path environmental variable, and it's pointing towards this directory, which is currently listed as available to us in Gazebo. And we added this directory, which is also right here. So if we blew up this Gazebo model path variable and we removed these paths, then we would not be able to access any of these models here, which would mean that we wouldn't be able to simulate our drone. So it's very important that we have the environmental variables set up. So let's actually pull up one of those paths. Let's go to course route, ArduPilot Gazebo, and let's go to models. And here you can see the complete list of models that we had available to us to insert into our Gazebo world. And in a later video, we might actually edit some of these files that characterize and define the models. But for now, this is the end of this video. Okay, so now we know how to load up a world file with Gazebo, and we know those world files contain things like the ArduPilot quadcopters that we want to actually simulate, but we still don't know how to control it. Well, let's just quickly review what is going on a real drone setup. On a real drone, you have the hardware, right? The motors, stuff like that. You have the firmware that controls the hardware. And then you have some higher level applications like a ground control station or a DroneKit Python script that can control the firmware that can command the hardware. All right, so that's just a review of that setup. It's a little bit different on a simulated environment, but we can think of the hardware in the real setup as being the Gazebo drone when we're simulating in Gazebo. So when we load up a world file that shows us that drone, think of that as just the hardware. We still need to launch the firmware to control that drone, and we know from the drone programming primer that that firmware is built for the CITL build type. Okay, and then just like normal, we can connect a ground control station or a DroneKit Python script to that firmware that will then command that Gazebo drone hardware. All right, so let's, in this video, actually start up our CITL vehicle and control it around in the Gazebo environment. So let's go to our virtual machine and let's pull up a terminal, and we're going to launch Gazebo with that world. So it's Iris Arducopter runway.world. All right, we'll launch that up and we should see our Gazebo drone sitting there on the runway. It's a lesser known Otis Redding song, Sitting on the Runway. And here we go. Now, here's our hardware, quote unquote hardware. We need to launch the firmware in order to control the drone. But first thing, let's just make sure that shadows are turned off. And you can actually configure this in the .world file itself. I'll show you that in potentially a future video. So let's pull up another terminal. And in this one, we're going to launch the CITL vehicle that will connect to this hardware. So let's go to course root, APM, ArduPilot, and then ArduCopter. Okay, and then we'll type tools autotest sim vehicle. And then here is the flag we have to pass in with this variable to let the sim vehicle script know that this is a Gazebo drone. So we'll do -F and then Gazebo Iris, and then we will type just --console -map, and we'll go ahead and do that, and we should see the real-time factor start to pick up quite a bit. And there's a lot going on here, isn't there? And yeah, you see the real-time factor getting much quicker. Okay, so I've just reorganized these windows to make everything fit. I am going to zoom out just a little bit so that we can see what the drone is doing. Okay, and just like a real drone takes a little bit of time to have the GPS get a lock and start influencing the EKF, it takes a little bit of time on the Gazebo drone as well. So here's our MAV proxy terminal. Let's go ahead and switch to guided mode guided. And let me just zoom in here so you can see the graphics. And let's type arm throttle, and you should see those props start to spin. There you go. That means we are now armed. I'm gonna zoom back out. Arm throttle. And then let's type takeoff 10, like we already know how to do from the drone programming primer. And that takes the drone off into the air at around 30 feet or 10 meters. I know it's not a perfect conversion, but. And then we can see where he's at in 3D space. And then here's our map of the drone. And if you're not seeing a map, again, go to View, Service, and then Microsoft Hybrid. And let's just click over here. Let's right click here. Let's say Fly to. And let's stay at an altitude of 10 meters. And let's hit OK. And we should see the drone start to go in that direction. Isn't that great? So this is a really cool way to use your SITL vehicle. Now let's just type mode RTL, and let's watch the drone climb to its return height. Now it's going back to the home GPS point, and now it's going to begin descending. There we go. And here we're seeing that we can actually control this SITL drone and watch how it behaves in 3D space. Now this is pretty cool, but we could have simulated everything we just did under a normal SITL simulation, right? So one of the primary reasons we wanted to use Gazebo was because it allows us to simulate sensors. And the sensor that we want to simulate is a camera. So now that we know how to fly the drone around, we're going to start learning things we need to learn in order to actually access that camera that is located on this drone. All right, so in this video, we are going to get into a little bit of ROS, shorthand for Robot Operating System. And you might be like, hey, why are we jumping into ROS all of a sudden? I was just getting comfortable with Gazebo. I was really getting excited about simulating that Iris Arducopter flight. Well, there's a couple reasons why we're jumping into ROS right now. And one is that Gazebo alone is decently powerful, as we've already seen. But Gazebo paired with ROS, that is when it becomes a superpower. And that's because ROS actually enables us to access sensory data in the simulated Gazebo world, things like a camera feed that we can perform computer vision with. And we can access the camera feed in a DroneKit Python script to control our SITL Gazebo drone. So ROS is allowing us to simulate a camera feed in a DroneKit script. So that's pretty awesome. So now that we know that, ROS is important to us for simulating computer vision based flight, and it makes Gazebo a superpower, what actually is ROS? Well, ROS is an open source meta operating system for your robot. It provides the services you would expect from an operating system, including hardware abstraction, low-level device control, implementation of commonly used functionality, message passing between processes, and package management. It also provides tools and libraries for obtaining, building, writing, and running code across multiple computers. And if you want to learn more about really the nitty-gritty and get into the weeds a little bit with ROS, you can check out this link at the wiki.ros.org. But we are going to sort of stay in the ROS basics world right now. We're just going to cover the basics. So there are three really core things in ROS that we need to be aware of. One of that is node. So what is a node in terms of a ROS network? Well, a node is a script or executable that performs some task on the ROS network. Okay, so then what is a topic? Well, a topic is just a special type of message the nodes can either get data from, that means that they are subscribing to that topic, or the nodes can post data to a topic. That makes them a publisher. And then the message, well, that's just the individual messages being sent to or from the topic. Now, I know with me, myself, I have a hard time, taking word definitions and actually understanding what that means. So here's a little diagram of that last slide. So here we have node 1. It's a publisher. It is publishing data to this topic in the purple box. And node 2 is a subscriber, so it's pulling data from this topic. And then this little message here, that is symbolic of the data that node 1 is sending to the topic, and then that node 2 is absorbing into whatever it needs the data for. And then node 1 would just keep sending data over and over and over again. And to get a little bit more specific, this is going to be kind of what we are going to be doing with ROS. So node 1 in our situation is going to be a Gazebo ROS camera, and it's publishing data, and it's publishing a single frame. Every time it gets a frame, it's publishing that frame to this topic, and this topic is going to be called raw image in the purple box. And then node 2 is going to be a DroneKit OpenCV script, and it's subscribing to this raw image. So it's going to take in this single frame, do some computer vision logic on it, and then make some commands to the simulated Gazebo drone. And then frames will just keep coming in and in from that ROS Gazebo camera. All right, so that is some of the extreme basics of ROS, but here are a couple notes that we should make about ROS in terms of how we're using it and learning about it in this course. So while ROS can be used with ArduPilot, we are only learning it to really unleash the power of Gazebo simulation. Okay, so now we should have Gazebo all installed. We should have ROS all installed. So now in this video, we are going to launch both of them together. But before we do that, let's pull up a terminal. And normally, up to this point, we've been launching Gazebo the normal way, right? Just Gazebo and then the name of the world we want to launch. So let's just do Iris Arducopter runway.world. And you might have already noticed this, but let's look at the verbose output in the terminal. So we see a ROS node for Gazebo has not been initialized. Unable to load plugin. Load the Gazebo system plugin lib Gazebo ROS API plugin in the Gazebo ROS package. So what does this all mean? This means that within this world file of Gazebo, we're trying to do some ROS stuff. But since we're launching Gazebo just with Gazebo alone, we're not getting access to that ROS stuff. And what is that ROS stuff I'm talking about? Well, this is referring to the camera feed that is attempted to be initialized when this world file is initially launched. But the camera can't initialize because there's no ROS network up and running. So how do we get around that? Well, you should already have something called Gazebo ROS already installed. So let's pull up a terminal and let's type in ROS CD. That stands for ROS change directory, and that just takes us to a particular ROS node. So let's go to Gazebo ROS. Okay, so what do we have here? Let's go into the launch directory. And if you don't already have one created, let's go ahead and type sudo copy and then empty world, and let's make a new launch file called iris_world.launch. And that's if you haven't already done this. But what are all these launch files? Well, when these launch files are called by Gazebo ROS, it initializes both Gazebo and the ROS network. Okay, so let's peek on the inside of one of these. I'm going to go into iris_world.launch, and you'll have to sudo into this. Okay, so all of this is initializing both ROS and Gazebo. It's launching both of them. If you'll go down here, we can see that we have arguments that we can pass in or set for this launch file of ROS. And here we have world name. And what we're going to do is type in our own world name as the default. We're going to type aruco_landing.world. And we'll save that. So what does that mean? Well, if you remember in our ArduPilot Gazebo worlds directory, we have a world called arucolanding.world. And this is actually what we're going to be using the most from this point forward. So we're going to make that the default world that this ROS launch file will initialize in Gazebo. Okay? So we're going to type Aruco landing, hit save, and then we'll get out of that. All right, let's just get a new terminal going. So how do we launch gazebo ROS. It's very simple. You just type ROS launch and then the name gazebo, just type RO and then hit tab, and then that should autocomplete for you. And now we have to call the launch file that we want, and let's call the one that we just created. That is irisworld.launch. And again, what this is going to do is both initialize the ROS network and launch Gazebo at the same time. All right, let's minimize this. And this should be the first time we're seeing this world. It's a little bit different than the runway we've been looking at. But this is the Aruko marker that we're going to be detecting and precision landing on. Okay, here we are. Now, let's pull up a terminal and let's look at some new commands, okay? So, ROS topic. Let's do ROS topic and list. And what is this going to do? This is going to show us all of the ROS topics that are currently being published and subscribed to. So, the topic that our camera on our drone is actually already publishing is this one right here. Camera color image raw. So we know on the ROS network that we have some frames available to us. So that's pretty awesome, right? Because we could not do this the way we were launching Gazebo before. There was no way to access the camera feed. And we can also do this. Let's type ROS topic HZ. That stands for like the frequency. And then let's type in that topic. Camera color, and then image raw, I believe. Yep. Okay, and this will tell us the rate at which this topic is being subscribed or published. So right now it's coming in at a pretty extreme rate. That's crazy. That's nowhere near the type of frames per second we'll be getting on the real drone, but we will be able to simulate that going forward. Okay, so we know we have our camera feed. We know that that topic is getting some messages. So how do we actually, view that with our two eyeballs? Well, let's pull up RQT. And this is a pretty cool little ROS thing. So what we can do is go to plugins and then visualization. And then let's type image view. All right, so we're image view. And let's pick the camera color image raw topic that we know our drone is currently subscribing frames to. Ooh, and there we go. We know that we can see here on the drone, it's zoomed in pretty close on that black part of that Aruko marker. And here we see that. So maybe we can try and launch this quadcopter up into the sky so we can really get an appreciation for how we can visualize the camera feed. So let's go ahead and launch a Cittal vehicle real quick. Let's go to course route, APM, then ArduPilot, ArduCopter. And let's launch our Cittal vehicle. And remember, we're going to have to do that with the -F and then gazebo-iris. That'll tell Sim Vehicle that this is a Cittal vehicle that is intended to launch to a Gazebo drone. So we'll hit enter. And again, we should also see the real-time factor speed up once our Cittal vehicle is up and running. Yeah, there it's speeding up a little bit. And I'm just going to reposition this camera real quick so that we can see it flying in the air. There's our camera feed. And let's see. And again, interesting, just like a real drone, we have to wait for the simulated drone to have its GPS get a lock and start being used by the EKF. So let's go ahead and wait for that. But in the meantime, let's type mode guided. Mode guided. All right. And I don't think we can arm yet, but let's try and type arm throttle. Need 3D fix. Okay, so we're still, okay, now we have that 3D fix. EKF2 is using GPS. So let's try and arm the throttle again. Throttle is armed. Let's type takeoff 10. And then let's watch the drone go up in the air, and there's our camera feed. So we can actually, access that camera feed of the drone. So this is really awesome, because this camera feed we're seeing with our eyes here, we're going to actually be able to capture this feed inside of a Python script that is going to have DroneKit, it's going to have computer vision, and those two things combined is going to allow us to perform a precision landing application. So this is awesome. If you're at this point, congratulations, this is a pretty big deal. Okay, so we are about to start getting into some coding, but to make that process a little bit easier for us, we are going to download an IDE called Atom. It's a pretty miserable experience having to, just code everything in VI or the gedit text editor. So we're going to open up Firefox and download that real quick. Just type in Atom IDE and then go to their website. And let's download the .deb file. And let's save it. And that'll take a little bit of time. We'll open up our little file cabinet here. Go to Downloads. And once this is complete, we will go ahead and double click on that guy. Okay, so now let's double click on that. And let's go ahead and hit install. And type in our password. All right, and then once that's done, that has installed to our machine. So we can go here to the show applications, and let's type in Atom. And let's click add to favorites. All right, and then let's go ahead and open that. And here is our IDE. And this is a pretty neat IDE. We're going to add one package so that our Python programming will be a little bit easier. So we're going to go to Edit, Preferences. Okay, and then we're going to go to Install, and we're going to type autocomplete, and then -Python. And we're going to install this, and this will make our programming in Python much, much simpler. Okay, that looks like that has installed, and that'll help with the auto-completion of like package names, variable names. Just it makes it a lot easier. But let's just give you a little taste of how it works. So let's go ahead and just take course root and drag that over to the Atom IDE. And you can see here, it puts it in the little tree drop-down format, and it's just super convenient. So we can drop down what we want to. Here's ArduPilot Gazebo. All right, so now we know how to create an example node and publisher in ROS. In this video, we're going to make another node, but this time we're going to be subscribing to that example topic that we created in the last video. So let's pull up Atom again and go back to this example package. So here's our example publisher. Now let's create a new file, and let's call it example subscriber. Okay, so same thing, let's put the shebang at the top. And we're also going to import ROS.py, not as anything, okay. And then also import this. All right, so now we need to make a function that will subscribe to that topic that we created in our example publisher. So let's say, let's create a function called subscriber. And it's very simple. Let's first initialize the node, ROS.py.init node. And what are we going to name it? Let's just name it example node 2. Again, lack of creativity right now. Okay, and now let's create the subscriber. So let's do ROS.py.subscriber. Okay, Now, what topic are we subscribing to? That's what we're putting right here. Well, let's go back over to example publisher. It's publishing example topic. This is the topic that we want to subscribe to. So we're just going to copy that and paste that over here. We're subscribing now to this topic. And what type of data is it? It is string data. Okay. And this is the tricky part a little bit. We're just going to say callback. What is callback? We'll stay tuned for that. Okay, and then let's just type rospy.spin. This will just loop this function. Okay, so what is callback? Well, callback we actually need to define. We're defining a new function. So if we detect a message that has been inserted into this example topic, we want to take that message and do something with it. So we've created the subscriber that's listening for the messages, and now this callback function is what we want to call whenever we have detected new data. So that's what this variable is here. This is the message that we will be receiving from our example publisher. Let's type string data equals data.data, and let's just simply print out that string data. All right, so every time we get a message from our example publisher, it'll call this function. This function accepts in the message. Let's actually call this message. It'll make it more clear. This is the message coming from example publisher. And how do we access the data from this message? We type msg.data, and then we print it. And then at the end of our subscriber, do not forget to put if name __ equals main. What are we going to do? Let's just call that subscriber function. There we go. Let's save that. Okay, so let's go ahead and catkin make that. Let's go to course root, catkin workspace, and then type catkin make. Now we're good to go there. Let's launch ROS core. Again, this is needed whenever we're launching ROS without that launch file, like how we launch Gazebo ROS. Now let's initialize, let's start up our publishing node. So ROS run example pkg, and then example publisher. Pull up another terminal, and let's do ROS topic list. We see that topic is currently being published. Let's get a little bit more info about that topic though. Let's do ROS topic info example topic. Okay, so we see the type, as we already know, is std_msgs/string. So this is the type of message that is being received by example topic. Well, maybe we want to get more information about this type of message. Well, we could type ROS MSG show and then that type of message. Okay, so this tells us this data, its type is string, and the name of that data is simply called data. So that's why in our subscriber here, we receive this message, and we that message has that .data attached to it. So it's the same name that is being showed in this ROS MSG show command, string data. If this was string hamburger, that would just be the name of the data. So we would type msg.hamburger here. You understand what I'm saying? Sorry. Okay. So now our ROS node for publishing is up and running. We need to go back to course root, catkin workspace, src. Let's go to our example package. Let's go into scripts, and we need to make the example subscriber executable again, just like we did last time. So we'll do chmod plus x example subscriber, and now they're both executable. So now let's type ROS run example pkg, and then the name of our subscribing node, example subscriber. And if this is working, we should hit enter, and we should see that string data that's being published from the publishing node written to the console. So let's hit enter, and there we go. Everything is working good. It successfully pulled in the data from that topic and published it, or wrote out that string to the console. So now that we have a general understanding of publishers and subscribers and how to create them in ROS, in the next few videos we're going to set up some Gazebo drone packages that will actually subscribe to and take action on that image data that is being written by that ROS Gazebo camera. Alright, so in this video we're going to do a quick introduction of Aruco markers, what they are, what they allow us to do. And this is going to be a high-level discussion. In subsequent videos, we're going to take a lower-level dive into Aruco markers. But here, let's just gain an understanding of them. So what is an Aruco marker? Well, they might look like a QR code, like that might be something you're familiar with, but it's basically a unique pattern of black and white boxes put together in a square matrix. And what do those allow us to do, though? If you want to get some nitty-gritty details, definitely head over to the OpenCV documentation. But just taking out the bullet points, if an Aruco marker is detected in a camera's frame, that allows us to obtain the camera's position in 3D space. And if we know where the camera's position is on a drone, then we know where the drone is relative to that marker. And this is very important for us because we are going to take that camera position and apply some error detection off of that. So let's just do a quick demonstration of what's going to be happening. It's my best Sal Khan impersonation. So here is a drone flying in the air. And let's say that we have a camera on this drone. We have a camera. And these dotted lines I'm drawing here, this is the field of view of the camera. So this is going to indicate one frame. So let's go ahead and draw that border of the frame in red. There we go. Let's get rid of this. Okay, and then we have the y-axis in blue. And then let's make the x-axis green, X. And then let's say we found an Aruco marker in this frame up here in the top left quadrant. Okay, so we found this in the frame. Now, and let's say the center of this Aruco marker, let's just make it that purple dot. So the distance from the center of the frame of the Aruco marker to the origin here, this would be our y error. And then the distance from here to the 0 point of x, this would be the x error. And what can we do with these errors? Well, we can send these errors or process them in a DroneKit script, which would then command the drone to fly in a direction which would minimize or lessen these errors. So this is the general principle of how we're going to use Aruco markers to accomplish precision landing in computer vision. Okay, so we're about to start coding our precision landing simulation in Gazebo and ROS, but before we do that, we need to make sure that our camera that's being simulated is as close to the real camera we're going to be using as possible. So in this course, we are using the PyCam version 2, but you might be using version 1 or a totally different camera. That is totally fine, but the same principles are going to be outlined here. So camera module 2, what we're looking for here is the horizontal field of view. So we have 62.2 degrees. So what we're going to do is modify our Gazebo ROS camera to have this horizontal field of view. Okay, so 62.2 degrees if you're using version 2. If you're using version 1, that would be 53.5, and you get the idea. So let's pull up our virtual machine, and let's pull up Atom that we just installed. If you don't have Course Root already pulled up into Atom, go ahead and do that. We'll drop that down, and let's drop down ArduPilot Gazebo, and let's check out models. All right, and one more, let's drop down Gimbal Small 2D Edit. Okay, this is 2D Edit, and then pull up the model.sdf. And these model.sdf files are actually the files that sort of build and put together the dynamics, the texture, the visualization of this model, Gimbal Small 2D Edit. And what's interesting is we can actually pull this up on Gazebo, and you can see what it would look like in Gazebo. So let's go to Insert, and let's just pull up Gimbal Small 2D Edit, click on here and drop it in the world. And here's our gimbal that we're editing. Right there. Oops. So this is what is going to be fixed to the bottom of the drone. And we can actually pull up that iris with ArduPilot right here. And you can see that when we pull up iris with ArduPilot, this gimbal is mounted on the bottom of the drone. So this is mounted here. So we're going to see how that joint is created whenever we pull up the SDF file of this iris with ArduPilot. But now let's hop back into that SDF file of the gimbal that has the camera on it so that we can configure that camera to be as close to our real camera as possible. Okay, so what we're looking for here is the camera tags, very specific ones. Here we go. Here's our sensor name. It's camera. All right. And here we have the horizontal field of view. And these tags define obviously the horizontal field of view, but it's in terms of radians. So we have to convert our degrees into radians here. So let's pull up a calculator. And so we have 62.2 degrees times pi, so that would be 3.14. And then divide that by 180 degrees. That's the conversion. And we have 1.085 radians for if we wanted to simulate the Raspberry Pi Cam version 2. If we wanted to simulate the version 1 camera, that'd be 53.5 degrees, I think is the horizontal field of view, times pi, which is 3.14, and then divide that by 180. And if you're using version 1 of the PyCam, that would be 0.9333 radians. All right. And so that's the horizontal field of view. The vertical field of view is automatically calculated through what we put here under the width and height section of our image. So we don't have to worry about vertical field of view. So what are we going to put here for image? Well, On the real drone, we're going to be capturing and processing images that are 640 by 480. So let's use those. Let's use that frame size on our gazebo camera. And then if you scroll down a little bit, you will see how this, when we launch this file, how a ROS topic is initiated. So what are we doing here? We're naming the camera ROS, and then we are creating a ROS topic that we publish frames to. So image topic name, we're calling it camera color image raw. We could change it to absolutely whatever, and it would still pull up every time we said ROS topic list. But this is where we define the topic name. And then downstream of this video, we're going to write some ROS nodes that subscribe to this topic, but that'll be for another video. Okay, so this is all the modifications we need to do to have our simulated gazebo camera be as close as possible to the real camera we're going to use in the real world. And again, that is for the Gimbal 2D Small Edit. Now, if we drop down the iris with ArduPilot and pull up that model.sdf, you will see here that in the model.sdf, there is the Gimbal Small 2D Edit. So this iris with ArduPilot model actually contains other models within it. So it's like a model of many models. Okay, so we're just creating here a joint that joins this model, the Gimbal 2D Edit, to the ArduPilot iris model. Okay, and then if we want to go crazy, we can show you how the world files are calling that iris with ArduPilot model. So the world we're going to be using most often is Aruko Landing, so let's pull that up. And then if we scroll down to the bottom, we'll see that it is calling the model iris with ArduPilot. So every time we load up this world file, it's going to load up this model, which has that camera that we just configured on it. So that's perfect. All right, so now we know a little bit about Gazebo and ROS. In this video, we're going to combine those two pieces of knowledge into one video. So what are we going to do? Well, we're going to create a ROS node that is going to do 4 things. The first thing it's going to do is subscribe to the Gazebo ROS camera topic image raw. Again, this is the camera that we have fixed to our Gazebo drone, and it's broadcasting the frames to image raw. So we're going to write a script to access that. The second thing the script is going to do is detect any Aruko markers that might be in the image. The third thing we're going to do is report the distance of the camera to the center of the Aruko marker. This will be a very important step for performing precision landing. And then the last thing to do in the script is draw the Aruko detection on a new frame and create a new topic called image new. So we're going to accept image raw, and then we're going to create a new topic, image new. Okay, so let's pull up our virtual machine, and let's go into Atom, and let's actually check out the ArduPilot Gazebo, and then let's go to Worlds, and let's open up Aruko Landing. Okay, and we're going to change the Aruko marker that we're using. So let's make sure the size is 0.2 and 0.2. And the Aruko marker, we're going to use marker 72. So let's save that. And now let's open up a new terminal, and let's actually launch Gazebo ROS with the ROS launch command. Gazebo ROS and the iris_world launch file. So this launches, again, both Gazebo and ROS. And we're doing this real quick so that we can investigate that image raw topic. Okay, so let's pull up a terminal. Okay, and let's type ROS topic list. And we should see right here, camera color image raw. Okay, that's good. But let's actually learn a little bit more about that topic. What is the message? What does it look like? ROS topic info, camera color image raw. And we see what type of message this is. This is sensor messages / image. Okay, so if we want to see what fields are available in this message, now we can type ROS MSG show and then that message. Okay, so we see we have a lot of different fields with this particular message. And we have things like the height of the frame, the width. Here on this right here, this is an array. An image is like an array of pixels, right? It might be 640 pixels tall and 480 pixels wide, and each pixel has an individual value to it. So that data field of that image ROS message is coming over in array form. We know, though, that in order to perform computer vision functions with an image, we need it to be in a NumPy array format. So we're going to download a repo that will allow us to easily change from a ROS image message into a NumPy array so that we can manipulate it in our OpenCV Python script. And then that repo will also allow us to easily convert a NumPy array image back into a ROS image message. So let's go on over to course root, Catkin workspace, and then go into the source directory. Okay, and from the source directory, we're going to type git clone, and this is going to be a repo from Eric Weiser, and the repo name is ROS NumPy, and we'll hit enter here. And let's do list, and we should have a ROS NumPy directory now. Now, the author of this repo created this repo to behave as a ROS package. So now we can use that ROS NumPy package, but first we have to type catkin make in order to make that new package official. Okay, so we have those introductory steps out of the way. In the next video, let's actually start making that script. All right, so now let's write that script that is going to accept the images in from that Gazebo ROS camera and detect the Aruco marker. So let's pull up another terminal. Let's go to course root, Catkin workspace, and let's go into the source directory. We have two packages right now. Let's create another one. Let's type catkin create pkg, and let's call this one Gazebo drone. So this is going to be a collection of scripts that are going to be used on the Gazebo drone. And let's type the dependencies. Let's type ROS.py and ROS.cpp and hit enter. Let's list it now, and we have the Gazebo drone package now. Let's go back to Catkin workspace and type catkin make. All right, there we go. Let's pull up that filing cabinet, and let's find that new directory we just made, Gazebo drone, and let's pull that up in our Atom IDE. All right, we'll drop that in here. All right, so this Gazebo drone, here's the package that we're going to be using for basically the rest of this section. So let's create a new folder called scripts. Okay, and let's make the file. Let's make this called trackaruco.py. Trackaruco.py. All right. So now let's write this script. Let's put the shebang at the top, and now let's do our imports. We have quite a bit of imports for this script. And we have ROS.py at the top, and this last one here is ROS NumPy. That is what we installed in the previous video so that we can deserialize our image feed. Now let's write some variables for this script. This first one, this is going to be a publishing object that is, as you know, we're taking into the script the image raw feed from the Gazebo ROS camera. Then we're going to make some modifications to that frame, and then we're going to publish that modified image to a new topic that we're calling here image new. And that second variable for the publisher function is the image. So that is which type of sensor message, which type of ROS message are we using. So that's the image. And then queue size, let's just do 10. Now we have ID to find. That is the Aruko ID that we are looking for in this particular script. And here we're doing 72. And the marker size we set up to be 20 centimeters in that world file. Now the Aruko dictionary, as we know, we've been sampling Aruko IDs out of the original Aruko library. So this script is going to need to know which Aruko library we are referring to. So we are just going to make a variable that will allow us to do that. And then we have our parameters. Now the horizontal resolution of our image, we set that ROS Gazebo camera to be 640 pixels, and then the vertical resolution to be 480 pixels. And then the horizontal field of view, if we're using the PyCam version 2, that's 62.2 degrees. And then if we want to convert that to radians, we have to multiply by pi and then divide by 180. If you're using version 1, that's 53.5. And the vertical field of view for the version 2 is 48.8. And for version 1, it's 41.41. Now, these two counters will come in handy at a later point when we're trying to sort of determine which marker size or which marker ID is best for our application. So every time we found the marker we're looking for, we're going to iterate once, and every time we didn't find the marker, we're going to iterate the not found count. All right, now we need to look up the camera intrinsics. So how we find that out with a real camera is we run through a calibration process to find the coefficients of the intrinsics. So we need to simulate those intrinsics for our ROS Gazebo camera. So we have these two arrays we need to fill out, the distortion coefficients and the camera matrix. How do we find that for the Gazebo camera? Well, it's easy enough. Okay, now let's go ahead and run ROS launch Gazebo ROS and then iris. This will launch that topic that we need to see in order to find the intrinsic values for our Gazebo ROS camera. So let's get Gazebo up and running. Now we're looking for ROS topic list. We're looking for what is the output of the top topic there, camera color, camera info. So we can type ROS topic echo and then list out that topic. Okay, here we go. This is what we need here. That D, that stands for the distortion coefficients. So those are all zeros for us. So let's just copy that and paste that in to our dist_coef variable in our script. Now let's look for the camera matrix values. Let's go back in here, and we're looking here at the numbers that have the K and the colon. So the first three values, let's copy here, and then let's paste into those brackets in the camera matrix. Now let's go back, let's get the next three values, and then let's paste that into the second comma delimited square brackets. And let's grab the last one, which was just 0, 0, 1. All right, and again, when it comes to the real world, we're going to actually have to find these values by calibrating our camera, but for now, this is good. Now we need to convert these arrays to NumPy arrays. So that's what we do here. Now let's start making our functions of this script. Let's make the subscriber, and remember we're subscribing to that camera feed from the Ross Gazebo camera, which is image raw. Okay, so we have initialized the node. This is called drone node. So when we start this script, it'll list drone node as running, and then we're going to subscribe to that image raw topic. And our callback, we're calling message receiver. And then rosspy.spin will just keep looping over the subscriber function. Now let's write that message receiver function. That is our callback function. So every time we receive an image from that Ross Gazebo camera published to that image raw topic, this is what we're going to do with it. Okay, let's first import some global variables into our function script that we will need. And now let's say if time.time minus time last is greater than time to wait. Let's first define what these variables are. Okay, so time last and time to wait. So remember in the past when we ran the Ross topic HZ on the image raw topic, and we saw it was running at like 370 times per second. Well, on the real drone, we're not going to get anywhere near 370 frames per second. Maybe we'll get around 10 frames per second. So we want to simulate our scripts as if we're only getting an updated frame rate of 10 frames per second. So what are we doing here? We're saying time to wait, 0.1 seconds, or 100 milliseconds. So if the current time, time.time, minus the last time is greater than 100 milliseconds, then we can run through this logic. So this will prevent us from having a frames per second of 370, which is just not realistic. Okay, now let's start off processing this message. So the first thing we're going to do is take that message from the image raw topic, and we're going to quote-unquote numpify it. So what that numpify function does is input a Ross image message, and it will output a NumPy data array, and we need our images to be in NumPy format to use them with our OpenCV functions. Now let's just convert that image to a gray image, and that's with the convert color command. And let's initialize IDs as nothing. Okay. Now let's type this here. Let's type aruco.detect markers. So what are we doing here? Well, we're feeding in that gray image, and we're telling this function that we're using the original Aruco dictionary, and we're passing in some parameters. So what this function does is it passes back all of the corners of the Aruco markers that are detected within the frame that we provided. And it's going to also tell us the IDs that it found. So we're hoping that one of those IDs is going to be 72, since that's what we are looking for. So now that we have those objects, let's try and do some logic off that. So let's try if IDs is not none, meaning there are actually IDs in that variable, and IDs at the 0 index is the ID to find that we're looking for, then let's perform this block. Okay, let's type this out. That's a long one right there. So we're going to use the function aruco.estimate, sorry, that should be a T, not a G, estimate post single markers. So we're passing in our corners variable. We're passing in the marker size. In our case, we already defined that to be 20 centimeters. And now we're passing in our camera matrix and distortion coefficients that we found. And that returned variable, RET, actually has a lot of information in it, so let's try and pull that out. So the rvec, that is the rotation vector, and then tvec, that is the position vector. That's the main one we're interested in right now. So tvec, that is telling us the distance in centimeters that our camera is away from the Aruco marker. Okay, and those are all strings now. So let's just make something called marker position, and let's just make a string that shows us all of those values. All right, now what we're going to do is actually modify that image raw that we input into this function. We're going to say aruco.draw detected markers. We're going to pass in MP data. What is MP data? Well, that is the image raw in array form, okay? And so we're going to pass in that image, and we're going to pass in the corners of the detected Aruco markers. So that is going to draw a little border around the detected Aruco markers on that image. Then the next thing we'll do is say draw axis, and this is going to draw the X, Y, and Z axes on this same NP data image. And we're passing in the image and our camera matrix and distortion coefficient, rotation matrix, position vector, and 10. So then we're doing cv2.putText. And there's a lot going on here. I'll list what those variables that we're passing into that putText function are above. So the first one is the image, MP data. The second thing is the text that we want to draw on the image. So we're just going to draw that marker position variable onto that image. And then the next one is the position that we want the text to be located. And then after that, we have the font face. Let's just use 0. And then font scale. Let's actually up that to 0.7. And the next one is color. We have 255, 0, 0. So that should turn up red. And then thickness. Let's make that a little bolder than we have listed here. Let's say thickness equals 2. All right. And now if we're in this loop, we know that we actually found the marker we're looking for. So let's say found count equals found count plus 1. If we weren't in that loop, then we didn't find our marker 72. So let's say not found count is not found count plus 1. And then let's run this exception block. If there's any problem that went on, let's write except exception. Then we're actually going to type as E, and then print target likely not found, print the exception, and then we're going to iterate not found count. Okay, so we did a bunch of things to that raw image that is currently under the variable MP data. We put the marker position on that image, we drew the axes, and we drew the markers. Now, that is currently in NumPy format. What this rnp.messageify function will do is convert that back into a ROS message format. So now, new message, that variable we have on the bottom of our screen, this is something that we can now publish to that topic, that image new topic that we created at the beginning of this script. So let's now publish that. Let's say new image pub.publish, and we're simply just publishing that image. And now time last, so we're now saving the time that we last ran this bit of code, and this will help us maintain our speed of processing this the data at around 10 frames per second, which is modeled after what we're likely to experience in the field on the real drone. Okay, and then else return none. That is just saying if not enough time has passed, if it hasn't been 100 milliseconds, then don't do anything in this message receiver function. All right, so now we are just basically done. Let's type one last thing that will call this subscriber function. Let's say if name equals main, we're going to call the subscriber function. And then accept rosspy.rossinterrupt exception, and we'll just type pass. All right, now that we have the script all finished, let's go ahead and test it out. All right, let's go to course root, Catkin workspace, and we need to update our workspace with the changes we've made to that package. So let's type catkin make. All right, there we go. Now we need to make that script that we just wrote executable. So let's type chmod +x, and then let's provide it the path to that script. So it's source gazebo drone scripts, and then track Aruko. We'll do that. And then, so now let's go ahead and launch our gazebo ROS drone. So we'll do ROS launch gazebo ROS, and then iris_world. This launches gazebo ROS. And let's pull up another terminal after everything quiets down. Let's pull up another terminal, and let's start the CIDL firmware. So let's go to course root, APM, ArduPilot, ArduCopter, and let's initialize CIDL. Okay, this will take a little bit of time to get it up and running. And while that's taking place, let's reorganize everything. Okay, so the CIDL vehicle is still booting up, but let's go ahead and take a peek at which ROS topics are currently available. All right, so we have image raw, but we don't have the image new yet. That's because we haven't started that node. Let's go ahead and start that now. Let's type ROS run, the name of that new package we created, gazebo drone, and then the name of the executable, the name of the file, that's track Aruko. Let's hit enter here. And now let's pull up the CIDL terminal that has mav proxy, and it looks like we're ready to launch. So we'll type mode guided, and let's do arm throttle. Let's take off into the sky at around 3 meters. There goes the drone. Now let's pull up another terminal, and let's launch RQT. Okay, so this is the normal image. This is the unfiltered image that the Gazebo ROS camera is providing, image raw. Now, if we pull up image new, we should see that it has drawn the border around the detected Aruko marker. It has the axis drawn, the axes drawn. So blue is x-axis, y, or the green is y-axis, and the red is the z. And we're also reporting the error, or the distance from the camera to the Aruko marker. And these are in terms of centimeters. So we're off around 10 meters in the x direction. We're off around 20 meters, or 20 centimeters in the y direction. And then since we know the absolute size of this Aruko marker is 20 centimeters, we can actually see how far away we are from the target, and that's what z is. So we're about 4 meters away from this target. And if we pull up a terminal again, we can do ROS topic list, and let's look for our new topic that we created. There we go, camera color image new. So there you have it. You successfully created a script to input the raw image and then perform some Aruko computer vision logic on it to detect the Aruko marker and get some position coordinates. This is a fundamental step that will help us in the next script we're going to make, which is going to be precision landing. All right, so in this video, we're going to get into a little bit of simulation and Gazebo. So what is Gazebo? Well, Here's another by-the-book definition. Gazebo is a 3D dynamic simulator with the ability to accurately and efficiently simulate populations of robots in complex indoor and outdoor environments. But wait, there's more. Gazebo offers physics simulation, a suite of sensors, put that one in italics, that's an important one, and interfaces for both users and programs. So basically, Gazebo is a simulated world that obeys the laws of physics, and this is where we can test robots or drones. So what can we do with Gazebo? Well, it's pretty cool. We can actually fly the Autopilot firmware, the real code, on a simulated drone in the Gazebo world. Now, if you took the drone programming primer class, you know that the simulated drone is called CITL. So we're basically connecting CITL with Gazebo, and we can test that simulated drone in the 3D world. And if you look on the right with that picture, that is actually a picture of the 3DR Iris, and that is sort of the standard drone model that is used for Gazebo to test Autopilot firmware. So what else can we do with Gazebo? Well, we can, just like we could in the drone programming primer, we can use and test Python DroneKit scripts on our computer to actually control the simulated drone. Now you might be saying, cool, this was already a thing we could do with CITL. Why do we need to, visualize it? Well, for one, the Gazebo physics engine is very, very impressive and is maybe a little bit more realistic. But the other very important thing about Gazebo is that you can simulate various sensors and experiment using them to control or influence flight. Okay, so why do we need Gazebo in this course? Well, we know that for our capstone project, our Tacocopter, precision landing is going to be a very important element of that mission. So Gazebo is going to help us test our precision landing scripts. We can actually access that simulated camera feed right in a DroneKit script where we can do some OpenCV computer vision based control on the drone. So basically, Gazebo is paramount for testing our OpenCV precision landing scripts and before even using it on a real drone. So what are the benefits? Well, this is kind of just recapping, but it saves time. Like, it really saves time. Just imagine that you have this new OpenCV script that you want to use with DroneKit to control the drone, and you didn't have a way to test it, so you just had to go out to the field and test it on a real drone. Well, you go out to the field, it takes 10 minutes, 15. It takes another 5 to make sure all the sensors are working correctly, and then another 5 whenever you try and run your Python script and you have a syntax error. So, it just really allows you to rapidly prototype right from your computer, so you don't have to make or find all those mistakes out in the field. It definitely saves money. Whenever you're experimenting with new DroneKit Python scripts that'll actually control the drone, those situations have a much higher likelihood of you crashing the drone for the drone doing some crazy behavior that you didn't expect. Well, we want to find those crazy scripts in the simulated world before we go out to the real world. And it's the last one, save a limb, kind of tongue-in-cheek, but if the drone did go crazy out in the field while you're testing a new script, well, you have, as many in the Autopilot community would say, you have a Psycho Wasp drone that's just out of control, and it can be very dangerous. So again, you want to be able to isolate those crazy flights in the simulated world. Okay, so Gazebo does require a decent amount of computer hardware. Let's go over what that is. So with memory, or the RAM, I would recommend 4 gigabytes. That's kind of the sweet spot. You could obviously go more, but at 4 gigabytes of RAM, you're getting a lot of the good behavior out of Gazebo. I've tested it with 2 gigabytes of RAM, and it works. It's kind of pushing it a little bit, but it's still maybe getting, 70% of the performance. At 1 gigabyte, I mean, it still runs, but it is with pretty bad performance. And what do I mean by bad performance? Well, the rate at which the simulated world is playing is maybe at like 20% of a real-time speed. So it looks like everything's moving in slow motion, which is fine if you have the patience for it, but I personally don't. Processors. Again, 4 cores is probably recommended. I have also tested with 2 cores, and it seems to work pretty good still with 2 cores. It's not the perfect performance, but it's still doing a good job. With 1 core, it also runs, but again, with bad performance. So if you have the recommended computer hardware available to you, definitely use that. If you don't, you might have to experiment around a little bit. Now, the required operating system is actually Linux. So if you have a Windows or Mac PC, you are going to need to set up a virtual machine. The suggested distribution is Ubuntu 18.04. It will work on other distros, but that is what we will be using in this course. All right, so how should you go about approaching this gazebo section? Well, you're likely one of these 2 people. You're either a drone programming primer graduate, shorthand DPP, or you are new to the dojo, or you haven't taken that course. Well, if you are a drone programming primer graduate, then good news. You should already have an Ubuntu virtual machine and VirtualBox already configured. You have knowledge of DroneKit scripts, and you have dependencies like DroneKit, MavProxy, ArduPilot, and other things already installed on that image. So this course picks up from the end of the drone programming primer. So if you've already taken that course, you can simply use that virtual machine from the drone programming primer to follow along in this course. If you have not taken the drone programming primer, well, you're going to need to set up a Linux virtual machine. So I am actually providing access to 2 already configured virtual machine images. And with those, you're going to be able to just download those from my Google Drive and then import them into VirtualBox. So the first image is going to be the virtual machine that is from the end of the drone programming primer. So you've already downloaded everything like MavProxy, PyMavLink, DroneKit, and ArduPilot. So those dependencies are already resolved, and the DroneKit scripts are already written. So that is the first image. And the second image is the virtual machine solution key for this course. So every script we're going to write in this course has already been written and tested, so you know it works. And all of the dependencies we're downloading in this course have already been installed and resolved on this virtual machine image. So here's what I recommend you do in this section. You should download both images from my Google Drive, and you should then create virtual machines for both of those in VirtualBox. Then you're going to use that first image, the one that is the end of the drone programming primer, to write along with the scripts in this course. So you're going to write the scripts, and you're also going to have to install all of the new dependencies in this course, things like Gazebo and ROS. Then you can use that second virtual machine image, the solution key, for investigating any of your mistakes. Maybe you were trying to code along with the video, but you did something wrong. Well, you can check out that same file you were trying to write in that second image, the solution key. Or maybe you're having a difficult time resolving a dependency. You can also check out how those dependencies are situated in that second virtual machine image. So in the next video, I'm going to walk you through how you can actually import one of those images into VirtualBox. It's going to be a .ova file, and it's pretty cool. You don't have to download, a fresh install of Ubuntu or anything like that. You simply just import that OVA file, and voila, you have a new virtual machine on your computer. Okay, so in this video, we are going to download VirtualBox. What is VirtualBox? Well, that will allow us to run a virtual machine on whatever operating system you're using. So head on over to virtualbox.org/wiki/downloads. And then here, based on what operating system you have, click on that. So I'm on a Windows machine, so I'm going to click click this, Windows Hosts, and it's going to start downloading the installation file. And then once that's downloading, go ahead and click on that, and that'll start up the installation wizard. So we'll click Next, Next, and let's see here. Let's have all of these check marked. And then we'll read this warning. It's just telling us that our network connections will temporarily be disconnected, so we'll hit Yes here. And then we'll click Install. So that'll take a little bit of time to download, and then you'll click Finish at the end. And once that's finished, you should be able to go in your search bar and type VirtualBox. And there it is. If you right-click it, you can pin it to the taskbar so that it's always available here. That is, if you're on a Windows machine. VirtualBox should work the same if you're on a Macintosh or Linux computer as well. So in the next video, we're going to set up a virtual machine that we're going to use in this section to perform our gazebo simulations. Alright, so in this video, we are going to set up our virtual machine that we'll be using to perform our gazebo simulations for our drone. In the lecture notes for this video, you will see links for a Google Drive to 2 files. Both of those files are pre-configured .ova files that you can simply import into VirtualBox. And when you import them, you have a virtual machine ready to go. The second Google Drive link I have listed, that is going to be the solution key environment. So every script that we're going to write in this course is already pre-written and is located in that virtual machine image. And every single dependency that you will need to run the code is also already pre-installed. That first Google Drive link is actually the end point of the drone programming primer. Feel free to download both of those images and import both into VirtualBox so that you can use that solution key if you get stuck in the virtual machine that you're using to write all the scripts. And so once you've downloaded those OVA images, how would you import them into VirtualBox? Well, you would click File and then Import Appliance. Okay, and then here you would supply the path to that OVA image that you just downloaded. Yours will likely be under downloads. And these are pretty massive files, right? They're anywhere from 4 to 10 gigs. So we're going to click on the OVA image that we want to import, and then we'll hit Open. Then hit Next. Now let's name this. You can name it whatever you want. I'm just going to call it Taco Copter. And here, the CPUs, this you will have to change. This will be dependent on your particular computer. So what I recommend doing is supplying anywhere from 25 to 50% of the CPUs that are available on your computer for your virtual machine. So if you have 8 CPUs on your computer, maybe give anywhere from 2 to 4 CPUs for your virtual machine. And use that same rule for the RAM. So if you have like 16 gigs of RAM on your computer, then maybe give anywhere from 4 to 8 gigs of RAM for your virtual machine. And then we'll keep these things all checked. And let's also hit reinitialize the MAC address of all network cards. And then we will hit import. And this will start creating that virtual machine that we will store in VirtualBox. And that'll take a little bit of time to import, so just wait for that to finish. All right, then once that's finished importing, you have your new virtual machine here. Again, I suggest importing both of those images, one for the solution key and one for the environment you're actually going to write the scripts in. But then we would just double click on that virtual machine to boot it up. And here we go, we're loading our virtual machine. And here we go, here's our login screen. Our username and password are both Drone Dojo. And here we are, here's our environment. All right, so in this video, we are going to go ahead and install all of the dependencies that are required to run the scripts in this gazebo section of the course. Now, first thing we're going to do is install OpenCV, and we'll paste in this command here on a terminal. We are in our virtual machine right now, and I will grant access to this installation list of commands that we have to run. So let's hit enter here.